Hello, welcome. This video is a bit of a departure from my usual content. Normally, I upload videos that have been edited down from my live streams, so you can see all the fumbles and mistakes I make as I'm doing them. And I'm going to show you some coding in the second part of this video, but sped up and not the usual fare. In this video, I wanted to share something I learned when solving a programming puzzle from Advent of Code's 2018 event. For those of you who don't know Advent of Code, it's a series of puzzles that are released one day at a time from the 1st of December up to the 25th. Each puzzle has two parts. In 2018, the Day 11 puzzle asks you to generate a 300 by 300 grid of numbers using a specific formula, and then find a 3 by 3 square in that grid with the highest total sum. Here I'm showing you just the upper left corner of that 300 by 300 grid because showing all 90,000 of them is not practical. So the obvious or the brute force way to do this is to take each 3 by 3 section, add up the numbers, and then move on to the next and add up those numbers and then just repeat for the entire grid. While you're doing this, keep track of which one has the highest sum and you get your answer. Now, I'm about to spoil part 2 of the puzzle, so pause here if you want to solve it on your own. I'm putting links below. Okay, so part 2, the second part of the puzzle, you have to find the highest sum of any size square on the grid. Whether it's 2 by 2s or 1 by 1s, any size at all, basically, all the way up to 300 by 300. And the answer is not just the whole grid because there are negative numbers. The brute force way still works, but it takes a very long time because you have to do the entire grid for every size. So in this video, I wanted to talk about a concept called a summed area table, which should make things go faster. A summed area table is a very simple solution to the puzzle, and it's really fast. It allows you to calculate the sum of any rectangular region of a grid using only 4 numbers. So how does it work? And maybe more importantly, how do you build it from your original data? The summed area table is computed from the original table, with each value in the table being the sum of all the values above and to the left of itself, plus itself. We could just add up the values in the data table, going through it step by step and placing the result in the summed area table, but that seems very inefficient and slow. The good news is there's a more clever way to fill the table, and by talking through how it gets created, that makes it easier to understand how to use it to solve the puzzle. Let's say we wanted to find the value that goes here on the right. We know that it has to be equal to the sum of all the numbers shaded in blue on the left. We can actually use the properties of the known values in the summed area table to calculate the next value. The value in the green box on the right is equal to the sum of the green values on the left. But we also want to somehow include the numbers from this column. The value in this green box on the right is equal to the sum of these other green values on the left, but now we're missing out on this row. If we simply add the 4 plus the 2 boxes, it means we're counting this region in the red box twice. So how do we deal with this problem? We can leverage the summed area table once again by realizing that the value in the yellow box on the right is equal to the sum of the duplicated area. Subtracting that value will even things out. So to get the number we're looking for, we add the 4 from the data table plus the number above and the number to the left of it in the summed area table, and then subtract the number diagonally up and left. And now instead of having to add up all the numbers in the data table, we can get our answers directly from these 4 numbers. And then we can fill in the rest of the table very quickly using this technique. So once we've done this, how do we get the sum of all the values in a randomly chosen rectangular region? Let's randomly choose this rectangle and see how we can do it using the properties of the summed area table. If we add up all the numbers in this region by hand, we get -17, so hopefully our summed area table will generate the same result. What we'll do first is to find the value that corresponds to the lower right of our region. This number in green is the one we're looking for. In other words, it has the same row and same column as the lower right value in our region in the data table. Because this is a summed area table, the value in the green box is the sum of all of these numbers that are shaded blue. Now, this area does include the region we want to sum up, but it also includes the 3 areas outlined in red, which we don't want in our answer. If we take a look at this yellow number, it's the number in the lower left of one of the regions we don't want to include, specifically this yellow shaded region on the left. And it's equal to the sum of all of those yellow shaded numbers. And this number over here on the right is equal to the sum of all of these other yellow shaded numbers on the left. But there's the same problem we encountered when building the table. If we subtract these 2 yellow numbers from the green number, we end up subtracting the sum of the squares in the red box on the left twice. Maybe you're already ahead of me here. So yes, if we can add the numbers back in once, it will make up for subtracting them twice. This number in green is the value we're looking for. If we add that back in, we should get our answer. So add the 2 green numbers, subtract the 2 yellow numbers, and we get -17, like magic. This works for any rectangular region. Let's write some code and see how this works in practice. First, I'm going to implement a helper function to build the initial data grid with a parameterized serial number. All this needs is a loop over all of the x and y pairs, and it calculates the power level at that location using the formula described in the puzzle. Because the grid indices are 0-based and the puzzle is 1-based, I subtract 1 from the x and y when accessing the grid. Next, I'll set up 2 calls to build the grid using the 2 sample values from the puzzle so we can check our answers. Here we can see the answers should be 90, 296, 16 for grid serial number 18, and 232, 251, 12 for grid serial number 42. Now I'll implement the brute force method. Let's start by keeping track of the maximum power level we calculated and create a variable to store the answer when we find it. We loop over every size and look at each x and y coordinate that's valid for that size. I had to subtract the size from the end of the loop so we don't access values beyond the matrix. Then, for each coordinate, we loop over every data grid value for that size and sum them up. If the sum we just found is larger than the current maximum power, then we found a new max. So we save it, and we save our current location and size as our answer. We have to add 1 back to the x and y coordinates because, again, the grid is 0-based, but the puzzle is 1-based. Let's build and run our code. I'm using the built-in time command to have macOS tell me how long the puzzle answer takes to find. Fast forwarding a bit, we get our 2 answers and a total time of 22.866 seconds. Now let's try the summed area approach. Before we can find our answer, we have to build the summed area table. So we loop over every x and y coordinate and use the technique described earlier to find the values for the table. Note that we have to check that we're not going off the left or top edges when we're computing the values, which adds a bit of code complexity. Once the summed area table is set up, we can re-implement the loop that finds the maximum power. This time, instead of creating the dx and dy loops, we use the values from the summed area table to calculate the answer. Again, we need to add some if statements to avoid trying to use negative numbers for the x and y coordinates. Updating the main function to use the new summed area function, and let's compile and run and see if it's any better. It found both solutions in 0.245 seconds. That seems like a worthy improvement. We can make the code cleaner at the expense of some extra memory usage. If we add a row of zeros at the top of the summed area table and a column of zeros to the left, we can shift the indices such that we don't have to use any if statement in our lookup statements. The first thing we'll do is change the summed area table to be a vector so we can push values instead of updating them in place. Next, we'll push a vector of 301 zeros onto it as the top row of the table. Modifying the Y range to go from 1 to 300, and likewise the X range, we'll create a row vector that will store one row at a time as we build it. Now we'll calculate the value for the summed area table by just doing lookups. We won't go negative because we're starting our loop at 1. We can get rid of all this code and just push the row we built onto the summed area table. The calculation can be simplified as well for the same reason. We will replace all of these lines of code with the 2 adds and 2 subtractions. Let's build this and run it. It takes 0.207 seconds, about the same amount of time, and the code is far simpler. Here's what the final code looks like. Please let me know if you have any feedback or questions, and thank you for watching.